All right, welcome back to factoring. We're going to look at um, 4 different types in this section, so we do have more problems. We've got 17 problems here. And one of the hardest parts of factoring is, obviously, when you split them up in sections like this and go, okay, this is your easy trinomial section, they're all easy trinomials. Well, when we mix them all up, which we'll do in the next section here, that's when it gets tough. So we have to, recognize factoring by, one of the easiest ways is number of terms. So far what we've seen is that the GCFs can be any amount of terms, and they're usually quite messy. Then we saw the trinomials were always the 3 terms in that form of x squared, no x, x. Whether or not the lead coefficient's a 1 is depending on which method you use. And then we saw the grouping ones were always those 4-termed. Well, this next method involves 2 terms, and it's always 2 terms, okay? So this next method is called difference of squares. Okay. And let's take a look at, first of all, what our perfect squares are. So have a list of perfect squares at the ready when you're taking a test, all right? Here's your list of perfect squares. 3. I'm just going to go down here because I didn't leave myself enough room, and on and on and on and on. What am I doing? Well, 1 times 1, 2 times 2, 3 times 3, 4 times 4. So if I took the square root of any one of these numbers, I'd get a nice whole number back out. The square root of 49 is 7. The square root of 100 is 10. Anything in between these would give me some sort of an icky decimal. So those aren't perfect. And also any even-powered exponent is perfect, and on and on and on. Anytime that I have an even one here, I can take the square root. I can take these all in half for the square root. X to the 5th, I can't. I get a messy fraction, 2.5. All right? So that's what a perfect square is. So this is really a difference of perfect squares, but we just say squares. Okay, squares means perfect squares. And so to recognize these, they're always 2 terms, never more. Okay, so this is 2 terms. They have to be perfect squares, and it has to be, all pieces of it have to be perfect squares. Every single thing has to be a perfect square, and you have to have a subtraction sign between them. Okay, then it qualifies. Difference meaning subtraction of squares. Here's a difference of 2 squares. Okay, so these all work out to be 2 binomials with 1 plus and 1 minus, and we take the square root of the front term in the front, and we take the square root of the back term in the back. Okay? So let's start out with this one. First of all, we have to verify that it is a difference of squares. Perfect square. Perfect square. Yep, I've got my 25 here, I've got my x squared there. So I've got 2 perfect squares. Okay, I've got exactly 2 terms, and I have a subtraction sign between them. Then I can break it apart into 2 binomials. I said that each has, 1 plus 1 minus, and I take the square root of each one. So the square root of w squared is w. And the square root of 25 is 5. So I put the square root of the front term in the front, both of them, and I put the square root of the back one in the back, and I'm done. Refoil to verify. Here's my w squared. My outside term is a negative 5w. My inside term is a positive 5w. And my last is a negative 25. Negative 5, positive 5, wipe each other out. All that's left is what I started with, w squared minus 25. Okay? Got real low there, sorry about that. Okay? What about this one? Well, let's look. Does it qualify? Does it have two terms? Yes. Is there a subtraction sign between them? Yes. Are they all perfect squares? No. 18 is not on my list. Okay? It has to be a perfect square minus a perfect square, so this one's not factorable. Okay? If this was w squared plus 25, that is also not factorable, because I don't have a subtraction sign between them. I have no rule like this that says this is for a sum of squares. It only works for a difference of squares. Okay, so don't be fooled on that one either. Let's do one more. Is this one perfect? Does this one qualify? Well, let's check it out. Do I have two terms? Yep. Is every single piece, now I have 3 pieces here, are those all on my list? Well, I've got an 81, I've got a 16, and I've got an even powered variable. So that works. And I do have a subtraction between them. So therefore, I have 1 plus 1 minus. I'm going to take the square root of all 3 pieces now. Square root of 81 is 9. The square root of a squared is a. The square root of 16 is 4. So I put the square root of the front one, which is a 9a, okay, in the front. And I put the square root of the back one in the back. And then I would refoil to verify. Ooh, fractions. I like it. I like fractions. I know most people hate fractions. 25m squared minus 36/25. Ooh. All right. Is it perfect? Well, 25 is on my list. M squared is on my list. I have 2 terms. I have subtraction between them. And this does happen to be a perfect square. Okay? If I would, honestly, I don't need my calculator, but if I were to use it, I can verify that it is indeed a whole numbered top and a whole numbered bottom on that. So the square root of 36 divided by the square root of 25, because each one of these numerators and denominators are perfect, it applies. So this is 6/5. All right, so this does apply, even though I know that I said it has to be a nice whole number, but also if the numerator and denominators are whole numbers, that works as well. 1 plus 1 minus. I'm going to take the square root of the front one. The square root of 25 is 5. The square root of m squared is m. So I'm putting a 5m in the front. And I've got this right there in the back. Okay? Should we check that one? Use integers or fractions. Let's see, do I have any other? I have 5m and 6/5. Okay, does it matter what order these go in? No, certainly does not. All right, so we want 5m plus 6/5 and 5m minus 6/5. Is that what we have there? Well done. All right. Ooh. Is 4096 a perfect square? I have no idea. Why did I do that? I don't know. Put that first. Check it out. 4096. Is it a perfect square? Yeah, it's 64. Okay? Now some of these are going to require more than one step, as this one will. So let's start. All right, so we have two terms. Each one's a perfect square. I've got an even power variable, and this one I checked. And I have subtraction between them. Perfect. I take the square root of the front one in the front. Now, whenever I have a variable, I just take this power in half. So that would be w squared. That would be the square root. Why is that? Well, this is the same as this exponentially, which is the same as that. And then the square root of 4096 was 64. Now some of you might think we're done because we did what we're supposed to do, right? But this is not finished. It says factor completely in the directions, okay? So whenever you form new pieces, you have to look to see whether or not you formed something that can be further factored. Now this one here can't be. We have a perfect square and a perfect square with two terms, but do I have an addition between them? That one I cannot break apart. But look at this thing. Perfect square, subtraction between. This can be further factored. So I'm going to leave this one alone because it's a sum of squares, which I have nothing for. But this one can be factored further into 1 plus and 1 minus. Square root of the front one goes in the front. Square root of the back one goes in the back. Now I have three pieces, and each of these are prime. I cannot factor any of these further. So I need all three of those. So we should check that one. Indeed we shall. So we have a w squared plus 64. And then we have a w plus 8 and a w minus 8. And it doesn't matter on the order of these three things. You just put them, you know, you've just got to have one of everything and then we're finished. Okay? I'm pretty sure my math lab has the capacity to interchange these. So if you happen to put your minus here and then split it up here, that doesn't matter. Okay? This one is the same, so I'll leave you alone on that one. All right, now we're into trinomials again. Now we've already learned how to do these with the easy method, but what I want to show you something. It's going to make it so much easier than if we were to do these the long way. Well, let's do it both ways. This one's actually fairly simple, but here, let me show you something here. Number 43. Number 45, sorry. Okay, look at this one. Okay, do you want to do 36 times 49? I don't. Look at this number that we'd have to try to factor. 36 times 49. We'd have to find all the factors of 1764, and we'd have to find some that add to 84. No, thank you. Okay, so I'm going to show you a different method. Now on this one's, I could do either way because the numbers are very low, aren't they? All right, so let's do the easy trinomial method that we had from before. We've got the x squared, x, no x stuff going on. We'll do it both ways and we'll just check it. I have a positive here, so that means they're the same sign. I've got my variable of a c, and my middle term's a positive, so they're both going to be pluses. I want to find factors of 16. So I have 1 times 16, I have 2 times 8, I have 4 times 4. And they have to add to the middle term of 8, so I'm going to pick this pair right here. Okay? And I can rewrite this as c plus 4 squared, because I have two of the same thing. Okay? So that's my easy trinomial method. But when they get to be icky, like the ones that I just showed you, we're not going to want to use this method or the AC method for that matter because it's too hard. So these qualify as perfect trinomials or perfect square trinomials. Okay? When they do, what's going on is if I take the square root of this front term, okay? Hello, where's my pen? There you go. And if I take the square root of the back term, and if I add these, or excuse me, if I multiply these, okay, so if I take 4 times 1 per 4, and I double it, it's always this middle number. Okay, and I multiply that by 2, gives me 8. Then it's a perfect square trinomial. Okay, all perfect square trinomials turn out to be something squared with the square root of the whole front term in the front, which is a c, the whole square of the square root of the back term in the back, and I match the sign on the inside. See how those match? I'm going to do a bunch of these because that might have gone a little bit. I'm not going to do the ones. Okay, let's just first of all see whether or not this qualifies as a perfect trinomial. We'll try this again. All right, so I have 3x squared plus 18x plus 27. Now I could use the AC method on this, but I'm going to be lazy. Okay, well, no I'm not, because this is not one of those. Okay, here this is not perfect. So we would first of all factor out the 3 and then we would proceed from there. So this is a bad example. Small, small, small. So we would take out the 3 and then we would have the easy trinomial left over. This is easy to factor. So let's look at that one. That one's too easy. So this one we could use the, the easy method. We've got, what do we have? We have x plus 3, x plus 3. So we have 3x plus 3 squared. So let's look at this one. Ugly, ugly, ugly. Now, is there anything in common with these things? No, there's not. There is nothing in common with the 36 and 84 and 49, so this method is not going to work. So here I could disregard my g's and use the AC method and then put them in the end if I wanted to. Or I can check for perfect square trinomial. All right. What's the square root of 36? 6. What's the square root of 49? I'm only taking my numbers. 7. Right? I'm just going to take the square root of that one and the square root of that one. I'm going to multiply these for 42. I'm going to double it for 84. It matches. So therefore, I have my square. I take the square root of this entire term. Square root of 36 is 6. Square root of c squared is c. And I take the entire square root of this one in the back. Square root of 49 is 7. Square root of g squared is g. And I match my sign in the middle. Done. Should we check that one? 6c minus 7g. 6c minus 7g. Okay, I'm going to expand it out for two of them, so I'm going to FOIL. My first term, I've got 36 c squareds. My outside term, I've got minus 42 cg's. My inside, I've got minus 42 cg's. And my outside, I've got a positive 49 g squared. This is supposed to be a 4. These combine for 84, negative 84. So it does work. Okay? This, to me, is super easy. I would be sitting here forever trying to find the factors of this ungodly big number here, which is 1,764. So if you've got enormously big numbers, check for perfect square trinomial because it's super easy and simple. All right. I don't know, do I have more of those? I do, I have one more of those, so let's try. No, I don't. That's it. All right, well, you've only got the one in there. Okay. All right, so onward and upward here. The next piece, well, I'm going to have to get rid of all this. The next piece is two different types. They're very related, but they're called sum and difference of cubes. Okay, so we need some formulas for those. So the first one here, we have a sum of cubes. Well, like we had the difference of squares, first of all, the first thing that we did when we were doing these was we were listing our perfect squares. So here we're going to have to list our perfect cubes. Okay? What are my perfect cubes? Come on, stupid pen. Well, for numbers, what do I have? 1, 8, 27, 64, 125, 216. Again, what am I doing? 1 times 1 times 1. 2 times 2 times 2. 3 times 3 times 3. Okay, cubing means 3 of them. Okay? Or on my variables, I have any power that's divisible by 3. Right? Because I can take a third of all of these. Just like on my squares, I took a half of all of them. So I wanted all numbers that were divisible by 2. Now I want all numbers that are divisible by 3 for my powers. Okay? And your formula for the sum of squares, the sum of cubes, is if I would have an a cubed plus b cubed, okay, here's both of these are cubes, and there's 2 terms, and I've got a plus between them, then this is always, kind of left myself no room here, so I'm going to go a little crooked, a plus b times a squared minus a times b plus b squared. Okay? Good. So now let's start. We've got a c cubed plus 64. The first thing that I want you to do is I'm going to want you, first of all, to verify that it's a sum of cubes, that it does qualify. Okay, we have 2 terms. I have a plus between them. This is on my list because my power is divisible by 3, and 64 is on my list. It's a perfect cube. It happens to be 4 times 4 times 4. So the first thing that I want you to do is I want you to rewrite them in this form. Okay, so this can be rewritten as this. 4 cubed is 64. Let's check that. 4 raised to the 3rd power is 64. So I'm just going to rewrite it in terms of cubes. Now I'm going to list what my a and my b are. Okay, my a is this thing here, whatever it happens to be. It's like this. So my a is a c, and my b happens to be whatever this is, which is a 4. It's going to make this so much easier. Okay? So now it tells me to do a plus b, right here, a plus b, and then it's going to tell me to do a squared. A is c, so I've got c squared. And then I'm going to match my sign of a minus. This tells me to take a times b, or I could do b times a. You know, I don't want to write c4, I want to write 4c. I'm not playing Battleship, right? And then I want to do a b squared. B squared is 16. 4 squared. I'm done. To check. Well, to check it's a little harder, right? Because I have to multiply my c through, then I have to multiply my 4 through, and I have to combine my like terms. But we better do that on our first one anyway. So to multiply my c through each term, I would have c cubed, that's my c times my c squared, then I have a negative 4c squared minus 4c squared, then I have a positive 16c. Now I'm going to do it again with my 4. 4 times c squared is a positive 4c squared. I'm going to stack my like terms so that they're easier to combine. Then I have a negative 16c there. And here I have 4 times 16, which is positive 64. Don't believe me? 4 times 16. I'd always have one person in the class that doesn't believe, that has to see everything, so there's got to be one of you out there. It's all right. I like people like that. Because you can't just be told, you have to understand, which I'm the same way. These are canceling, these are canceling. All that's left is what I have. So this is the answer that you want to put in MyMathLab. C plus 4 times c squared minus 4c plus 16, both in parentheses. All right, we have another problem. This one is not a sum of cubes, it's a difference of cubes. I've got a subtraction between them. I'm using the exact same principles here, just a different formula. So now I have a difference of cubes. And my formula is, if I would have a cubed minus b cubed, that would factor to a minus b, a squared plus ab plus b squared. Okay? So let's start. We've got our s cubed minus 27. All right, I'm going to rewrite that. Is 27 on my list? Better be. 3 times 3 times 3. Okay? I'm going to rewrite that as s cubed. I hate those s's. Minus 3 cubed. They look like 5s. Therefore, my a is s. My b is 3. So I have a minus b, and I have a squared plus ab or ba plus b squared. 3 squared is 9. Okay? Now I'd always have to check, I always have this trinomial left over, don't I? I have to see whether or not this is going to factor. This is one of those easy trinomials that's in the x squared x no x pattern. Well, what are my factors of 9? 1 times 9, 3 times 3. I have a plus here, so they have to add to my middle term, which is 3, but neither one of these do. But sometimes they do. You have to check. Because if they did, I'd have to break this trinomial apart, wouldn't I? Yeah, I would. Okay. Let's see. I think I'm just going to do, I think I'll just do this last one for you. It's the only one. No, I'm going to do the second to last one first of all. Number 75. That's that one. Do you see what I'm doing there? If I put my cursor over it, you can see which problem in the book it is. I kind of always have my book open to see what's going on. So this is the same type of problem, same form as chapter 6, section 5, number 75 in the book. This one's like number 67 in the book. This one's like number 79 in the book. Okay, so that's how I choose my problems too. All right, so let's start. The ones in between are all the same, so there's nothing new in there, I don't think. No, there's nothing new in there. Oh, well, there's that one. Okay, we better do that one. That one's different. 12, 13, and 14 are all the same, so I'm going to come back to this one. All right, I'm going to do this one first. I should check that to make sure that everything is the way it's supposed to be. All right, so let's check to see whether or not this is a sum of cubes. Is every little piece on there? Is 8 on my list? Is b cubed on my list? And is 1 on my list? 1, 8, 8 cubed. Bx cubed, yes, they're all. I have two terms with a plus between them, so this qualifies. So remember how we had to, before we had to rewrite it like this first? I want to do the same thing here, but now I have 3 pieces to rewrite. Okay, and 8 can be written as a 2 cubed, and a b can be written as b cubed, and a 1 can be written as 1 cubed, because 2 cubed is 8, this is b cubed, 1 cubed is 1. Now what I can do here is I can put these in the same set of parentheses. All right, so now my a becomes 2b. It's all of this. And my b becomes a 1. It's just this. All right. Now I'm going to go back to my formula. I have to get it out here. All right, my sum of cubes says I take a plus b, a plus b times a squared. Okay, so I'm going to square my entire 2b. I'm going to do this in pieces here. Minus a times b, well, that's just 2b, plus b squared, which is 1. 1 squared is 1. So now I'm going to have to clean this up a bit. So I've got 2b plus 1. And this, let's just go up here, 2b squared is equal to 2 squared b squared, which is equal to 4b squared. And that's done. Okay? Just be careful when you have a number in front of here. Your a is not 8b. Your a is 2b. Okay? Here your b was not 27, it was 3. So when you rewrite these this way, it becomes very clear what your a and your b are. If you don't do that, sometimes you can really mess up. A lot of people, that's probably one of the most common mistakes, is I see this, your a becomes an 8b, which it isn't. It's a 2b, so just be careful with that. All right, so we'll do these last two as well. All right, we have 3r cubed minus 192. All right. Now r cubed is on my list, but I guarantee you a 3 and a 192 are not. 3 is not. 192 is not. Now what? Well, I'm going to look to see whether there's a GCF. Is there something in common between these that I can take out and force it into that pattern? Well, let's take 192 and divide it by 3, and it's 64. So I'm going to take out my 3, which is my GCF. I can't take out any r's because this one doesn't have an r. So I'll divide both of these by 3. So all that's left here is the r cubed. And this is 64. And what I've done is I've turned this back binomial into a difference of cubes. Perfect cube, perfect cube. So it does qualify now. So this 3 just keeps going along for the ride. What was the cube root of 64? Do you remember how to do that on the calculator? If you don't, hit the math key. Cube root is option number 4. This is just in case you don't know what it is, if it's a larger number. So we've got 4. So we've got minus 4 cubed. So here my A is R, my B is 4. So I still have this 3, don't forget that. And now I have A minus B. And I've got A squared plus AB, which is 4R, plus B squared. So if I would take the time to remultiply all these things together, I would get back this piece right here. But otherwise, you're just putting all of this into MyMathLab. Okay? And I really don't want to do that. Please don't make me do that. Please don't make me do that. I'm too lazy. All right. I don't know if I need to do this one or not. I mean, these are both divisible by 3, and this is obviously a perfect cube. Let me just get it set up for you. I think you'll be fine on this one. It's the rewriting that's hard. I want to rewrite it as cubes, so it's a sum of cubes. Well, how do I turn b to the 6 into something cubed? Well, remember my rule on exponents. X to the a to the b is x to the a times b, right? So I can write this 6 as b squared cubed, can't I? Isn't that b to the 6? Using this rule, isn't this the same thing as 2 times 3, which is 6? And then I'm going to rewrite my 64 as 4 cubed. And I'm write my p6 the same way. So I've got p squared raised to the 3rd power. So here, my a is b squared, right? It's this whole thing that's cubed. And my b, unfortunate letters they've chosen, would be 4p squared. Okay, maybe we should do this one. We're almost done with it anyway, so we might as well. Okay, so we've got an a plus a b. B squared plus 4p squared. And then I've got a squared, which is b squared squared. Then I have minus b squared times 4p squared. I'll clean these up. Then I have plus 4p squared squared. I'll just use that one. Okay, I have the whole b squared. All right, now I've got to clean these all up. This front one can't be cleaned up much. So I've got b squared plus 4p squared. B squared squared, remember I'm using this rule here, would be b to the 4th. Minus, I'm going to put my number first, and I'm going to put these in alphabetical order because that's the way MyMathLab likes it. And here I'm going to square both of these. I'm going to square the 4 for 16, and I've got my p to the 4th. Okay? So that's how that works. I think that's it. I think we're done. So practice these. Let's see what's next. I always like to tell you what's next now. I don't know why. Why do I do that? I don't know. I think we're moving on to, where's my sheet here? We're moving on to 6.7, which is solving quadratics using factoring. So we're going to take a look at how to recognize what type of factoring problem we've been given and use it to, whatever technique applies to solve the quadratic. So I'm going to be talking a lot about quadratics and what does it mean. We're going to look at the calculator with the graphing component, the intercepts, all that good stuff. So that's going to be a longer section than this one, although this one was 40 minutes. So just keep practicing, practice, practice, practice. All right, and I'll see you for the next section.